I am unemployed and it's summer break, so I'm gonna make some videos on Lie algebras because I just took class. And the very first thing I'm going to talk about is interesting in its own right, associative algebras. An associative algebra is by definition a vector space over some field F with some sort of product. You can call it dot, or sometimes you just don't include it. I'll show you some examples here shortly. That is associative and bilinear. What are some examples of associative algebras? Well, you can look at the set of n by n matrices over some field F, denoted M of nF. This is an associative algebra with matrix multiplication, which is, bilinear. You can take the product of two matrices, A times B. And it satisfies certain properties, such as ABC is equal to A times B times C. That's associativity. But it's not commutative, right? In general, A times B is not equal to B times A. But it is associative, so M and F is an associative algebra. A second example that my writing is all in the way of is vectors with n components in your field F, denoted Fn, where you multiply two vectors component-wise, which is really weird to do because it's like, is it supposed to be the dot product? No, you don't really see this at all. I've never seen this product before in really anywhere, but it's technically associative, it's technically bilinear. So it turns Fn into an associative algebra, probably a less interesting one than the matrices. A third kind of associative algebra is if X is a metric space, you can look at the set of continuous functions over X, right? This is a vector space, which I'll kind of take for granted. And the product here is just multiplying two functions, right? F times G. And this thing is just defined not component-wise, but point-wise, right? F times G of X is equal to F of X times G of X. You just multiply two functions. It's associative. It's a bilinear product. And this third example is kind of interesting in its own right because of the Stone-Weierstrass theorem, which you might have seen from real analysis. It says if X is a compact metric space and A is a subalgebra of C of X. Well, it's C of X. C of X are the continuous functions over the metric space X. A subalgebra is a subset of an algebra that's also an algebra in its own right. So A is also an algebra contained in the continuous functions, such that 1 is an element of A. This is the constant function. And for all distinct points, P and Q in your metric space, there exists a function, H, depending on P and Q, in A, right here, your algebra, such that H of P is not equal to H of Q. Then the closure of this subalgebra is equal to all the continuous functions with respect to the sup norm. And this is a very famous result from real analysis. A couple of things to note. First of all, we're allowed to do the sup norm here because, why? X is a compact metric space. So every continuous function on X does obtain a supremum by the extreme value theorem. So the sup norm is finite for every continuous function. So this is a perfectly valid norm, specifically on C of X. I shouldn't say it's not the norm on X, it's the norm on C of X, the continuous functions. For example, you could say that A here is the set of polynomials, right? and let's say x is the interval from 0 to 1 closed. Then the Stone-Weierstrass theorem says that the set of polynomials is dense in the set of continuous functions from 0 to 1, a result more popularly known as the Weierstrass approximation theorem, and that just says that you can approximate any continuous function on the closed interval from 0 to 1 using polynomials, which is like super awesome. But this is a generalization of that, which is even cooler, whose proof you can find in my undergrad analysis textbook, Introduction to Analysis of Several Variables by Professor Michael Taylor. He is awesome, and his book is awesome, and you can find the proof of this there. But this is just an example of seeing where this idea of an associative algebra is used, not just in algebra, it's used in real analysis, it's used all over math. So that's why I think knowing what associative algebra is interesting in its own right, you know? So that was my very, very first video on Lie algebras.